Hello, today we're continuing in our A-level physics revision series, this time looking at telecommunications. We can of course communicate by using our voices, and somebody else can listen through their ears. In that case, sound is travelling from the voice to the ear. Sound waves are longitudinal waves, that is to say that the air in between the voice and the ear is vibrating backwards and forwards, and that's a longitudinal wave. So you've just got air molecules that are vibrating. But that's not necessarily the best way of communicating. You might be too far away to be heard. So now you need to use a microphone and a speaker. So here we are. And now we're going to use a microphone, and we're going to have a loudspeaker. How do they work? Well, my video on electromagnetism will give you the clue there. Basically what you're talking about is if you move a magnet, here's a magnet, a bar magnet, if you move a magnet in a coil of wire, a current will flow. Or you move a coil of wire in the presence of a magnet, a coil will flow. And so the way a microphone works is you have what's called a diaphragm, which is rather like a stretched piece of plastic, like, for example, a balloon skin. And in the middle you place a very small magnet, and then around it you have a coil of wire. Then if you've got sound waves coming, those sound waves are oscillating, vibrating waves, and as they hit this essentially balloon diaphragm, the diaphragm vibrates, the magnet itself which is connected to the diaphragm vibrates, and a vibrating magnet in the presence of a coil of wire will cause a current to flow. And that's how a microphone translates sound into an electrical signal. The loudspeaker is simply the same thing but in reverse. The loudspeaker takes the electrical signals from the microphone. The electrical signals are in the coil of wire. They're varying electrical impulses, and a changing current will cause a magnet to move. And so the magnet now moves, and that creates oscillations, and those oscillations will then cause the air molecules to oscillate, and oscillating air molecules emerge as sound. But of course all of that requires that the microphone and the speaker is connected by a wire. And once again that may be too far away. So now you may need the microphone and the speaker to be connected by telecommunications, which is when you send signals through the air. And that's what we're principally going to be looking at in this video. How do you send and receive signals through the air? Well, you use either a transmitter or an aerial, and in each case they're the same thing. They're basically just a length of wire. And what you do is you apply a varying, alternating voltage to this wire. And when you apply a varying voltage, then the voltage on the wire will change. And as a consequence, the electrons in the wire will be attracted to the positive end of the wire. So when the voltage is at the positive end, the electrons will all shoot up this way, and when the aerial is negative, the electrons will shoot down that way. And so the electrons are constantly accelerating up and down the wire. And what happens when a charged particle accelerates? You should know that generates an electromagnetic wave. And the frequency of that electromagnetic wave will be the same as the frequency of the electrons shooting up and down this wire, which of course is the frequency of this voltage here. And it's exactly the same but in reverse when you get to the receiver. The wave comes in, it causes the electrons in the wire to vibrate up and down, and that creates a voltage pulse which then can be sent off to the receiving equipment, like a television or a radio. So you can see that what we could do is to take the electronic signals, which are the, as it were, the analogue of the sound waves from your voice, the analogue electrical signals, send them to an aerial, and transmit a wave to a receiver. The problem with that is that the wave that would be sent would have the same frequency as the electrical signals, and the electrical signals would have the same frequency as your voice. And your voice is fairly low frequency, and low frequency radio waves don't travel very far unless they are very, very powerful. You need to get the frequency higher if you want the waves to travel any distance through the air. And this is achieved by adding the signal that you get from the microphone to what is called a carrier wave. And the carrier wave is much higher frequency. So you might have a carrier wave, which is simply a generated alternating voltage that looks like that. And then you might have your sound wave, which will be much lower frequency, larger wavelength, that looks something like that. And you essentially add the two together, so you get a wave which has this as its, what they call, envelope, and the high frequency wave, the carrier wave, looks like this. So you've effectively merged these two waves to form this wave, and that's simply called an AM wave, amplitude modulated. And it's amplitude modulated because the amplitude of the sound wave, which is the one you're trying, that's the signal, when added to the carrier wave, we modulate the carrier wave according to the amplitude of the sound wave. That's amplitude modulation. There's another way of doing it, and that's called frequency modulation. And what you do is you take your carrier wave and your sound wave, which of course has now become an electrical wave via the microphone, and what you do is you make the frequency of the carrier wave much more intense when the sound wave is at its peak, and you have a much lower frequency when the wave is at its at the lowest point. So what actually happens is that the actual size of the wave doesn't vary, but as you get to the peak here, the frequency is very, very, very high. But as you get to the bottom of the wave, the frequency becomes low. And then as the wave goes up again, the frequency becomes very, very high. So what is happening is that the amplitude of the wave remains the same. It's the same height throughout. But the frequency increases and decreases according to whether the amplitude is high or low. And that's called a frequency modulated wave, FM. Now, in the case of both amplitude modulated and frequency modulated, the signal, and this is the main signal here, will have what's called a bandwidth. For example, let's say that you're using 200 kilohertz as your main signal. Let's say that's 200,000 cycles per second. Does that mean that you can have another signal entirely separate at 201 kilohertz and send another piece of information? Let's say two radio stations, one at 200 kilohertz and one at 201 kilohertz. Will they be okay? The answer is no, because what happens is that you need to say the bandwidth is the amplitude of the signal itself. So if, for example, the amplitude of the wave, that is the sound wave, is say 20 kilohertz, most hearing goes up to about 20 kilohertz. So let's say that the amplitude of this wave is 20 kilohertz. Then you're going to need 20 kilohertz on either side of this frequency as what's called bandwidth. So plus or minus 20 kilohertz is the bandwidth for that signal. And consequently, you cannot have another signal within 180 to 220 kilohertz, otherwise it's going to interfere with this signal. So you've got to go, essentially, the next carrier wave that you can use is 240 kilohertz, because with plus or minus 20 kilohertz, that will go from 220 to 260. So this is going from 180 to 220, this is going from 220 to 260. And that means you can have two separate radio stations on these frequencies, and the bandwidth is taken care of. One way, of course, of getting more radio programs in your frequency spectrum is to reduce the bandwidth. And that is typically what happens with AM transmissions, because they use low frequency, high wavelength radio waves, and you can't fit enough on if you don't reduce the bandwidth. But if you reduce the bandwidth, you obviously reduce the quality of the sound, because the higher frequencies will no longer be there. So what are the differences between AM and FM? Well, an AM signal is more amenable to interference from other things that are generating waves. Like, for example, a motorbike going past might send out some kind of signal, and if you've got an AM wave, which you remember modulates the amplitude, then interference might add a bit to the height of the wave, and that of course is adding to the amplitude, and that means that when that goes to the loudspeaker, it's going to interfere and you're going to get crackling on the sound. Whereas if you've got a frequency modulated, which means it's very high frequency, then low frequency, then high frequency, it doesn't matter if bits are added on the end, because it's the variation in frequencies that matter, not whether there are some surplus noises. So frequency modulation is much better than amplitude modulation when it comes to interference. If we think about long wave transmission is usually in the frequency spectrum 30 to 300 kilohertz. So there is 270 kilohertz to play with. If we make the bandwidth 9 kilohertz, which essentially means 4.5 kilohertz either side of the main signal, then you can get 270 divided by 9 equals 30 stations in that signal frequency. Each of those 30 stations will have a bandwidth of 9 kilohertz, that is 4.5 kilohertz on either side of the main carrier signal. But of course, that means that your sound can only have a maximum range of 4.5 kilohertz, which means you're taking out all the high frequencies, and so the quality will be lower. Now let's suppose we try to put frequency modulated sound in this band. For FM, the bandwidth is 200 kilohertz, which equates to a maximum audio frequency broadcast of 15 kilohertz, which isn't quite as high as the 20 that you might expect if you were listening to someone in a room, but it's still pretty high. So the quality is going to be much better. But look at this. How many bandwidths of 200 kilohertz could you get in a 270 kilohertz spectrum? Answer: 1. You could only have one FM station on long wave. And for that reason, FM stations use the much higher frequency, which is at what's called VHF, very high frequency. Another distinction is that AM channels propagated on long wave, or even medium wave and short wave, will travel long distances. Frequency modulated on VHF will only travel relatively short distances. So you only need one big transmitter to cover a huge area for AM, but you need lots of transmitters over a shorter distance, each one covering a smaller area, in order to transmit on VHF. Now let's look at a further problem associated with recording with a microphone. Here's our microphone. It takes sound waves in and it generates electrical signals out. And as I said, what you do is you send that electrical signal to a speaker, and the electrical signal is then converted back into a sound wave. The problem is that as it transmits along the wire, all sorts of things can add sound to it, and that's called noise. Random electronic peaks will make variations and squiggles to the signal so that by the time it gets to this end, it's a good deal noisier, and so the sound that you get from the loudspeaker is not as good. Now there's a solution to that, and that is to send the signal not as this, which is called the analog signal because it's analogous to the sound wave that created it, but to send it as a digital signal. And the way you do that is that you have to create an analog signal to start with. There's no way round that. So you get your electronic signal, whatever it may look like, and that's the kind of electrical pulse that equates to and is the analog of the sound. But then as soon as possible, you feed that into an analog to digital converter, ADC. And what that does is it freeze frames, as it were, the signal that you get from the microphone, and then it digitizes so that you get a kind of digital pattern for this particular frozen frame. What that means is you need to know this is the voltage and this is the frequency. So you need to know the level of the voltage for each of the frequencies at a particular moment in time. And what you have to do is to decide how many steps up the voltage chain you want to go and how many frequency divisions along the frequency line you're going to make. The more you make of each, of course, the higher the quality and the nearer the digital pattern will reflect the analog pattern. But of course, the more data you'll have to store. So you store, for example, for each frequency division that you choose, you store this value as a digital number, where that means it will be 0 for 0, 1 for, as it were, 1, but then 1 0 is equal to 2, 1 1 is equal to 3, 1 0 0 is equal to 4, 1 0 1 is equal to 5, 1 1 0 is equal to 6, and so on. And so, depending on how many digits you're prepared to have in your digital signal, all of those digits are going to take up room and take up time to transmit. That will determine how many divisions you can have, and then the number of frequency divisions determines, again, how much in total of the signal you're going to have. But remember, this is just the digital signal for one freeze frame. A fraction of a second later, this signal is going to have changed. It's going to look differently. And so you're going to need to digitize it again and get the new digital equivalent of that signal, whatever that may be, however many divisions you have here and how many divisions you have here. And what you end up with is a series of digital numbers which reflect the height of the digitized signal for each frequency variation for one frame, and then another set of numbers for the frame which comes a fraction of a second later. So again, the decision is, how frequently are you going to digitize the picture? Once every second? Once every 10 seconds? Once every tenth of a second? Once every hundredth of a second? The more times you do it, the better will be the quality. But of course, the more times you do it, the more data you generate, and you've got to transmit that and store it. Now, a man by the name of Nyquist had identified some time ago, 80 years ago or more, that if you want to get a decent digital signal, which would produce decent sound from an analog signal, then you have to sample, that is, you have to take this frame shot at a frequency which is twice the highest frequency component in the original signal. So whatever the frequency is of the highest part of the signal, you have to do a freeze frame sampling at twice that frequency. And since the highest frequency that you can hear is about 20 kilohertz, you need to sample at twice that, and in fact that would be 40 kilohertz, but what you will typically see as a sampling frequency is 44.1 kilohertz. That tends to be a standard that you will see. And that means that we are taking 44,100 freeze frames per second and digitizing each of the frequencies according to the voltage for that particular freeze frame. And that's a lot of information. And that's why digital audio files are so big, typically 50 megabytes for a 3-minute song. So what are the methods of communicating? Well, if you want to switch on a light, the way we typically switch on a light is we have what's called a 2-wire system. We have a wire that goes to the light, and then a wire that comes back with a switch. And when you close the switch, the light comes on. That's just a there and back 2-wire system. And you might think you could use that for communication, but it suffers from a great deal of deterioration because the signal can be affected by all sorts of noise as the signal is transmitted along the wire. Now that can be significantly reduced by using what's called a coaxial cable. And in a coaxial cable, the out wire, which is the equivalent of this one, is what's called the inner core. That's just a copper wire that goes through the centre of the coaxial cable. The return wire is actually a kind of casing that goes round the original wire and is separated by, of course, an insulator so they mustn't touch. And so the signal goes out in the inner wire and then essentially returns in the outer shielding, and they are separated by an insulator. And what that means is that the signal is very much better protected from outside influences that might seek to change the current and thus interfere with the noise, the sound that you are trying to produce. And then, as we've seen, there is the radio transmitter, which transmits sound in all directions. You can have long wave, which is usually 30 to 300 kilohertz, and that will travel, well, it'll have a wavelength of about 1 kilometre. Medium wave is usually 300 kilohertz to about 3 megahertz. Short wave is about 3 megahertz to 30 megahertz. VHF, which is what we use for most of our radio transmissions, 30 to 300 megahertz. UHF, which is what we use for television broadcasts, is 300 megahertz to 3 gigahertz. And then you can have some microwaves, very exceptionally high frequencies, EHF, and that's 3 to 30 and sometimes even 30 to 300 gigahertz. If you take the VHF spectrum, in England we have a radio programme called BBC Radio 2, and you will often hear them say this is 88 to 91 FM. What they mean is it's 88 to 91 megahertz is the area of the spectrum in which this is transmitted. They don't mean that one signal occupies the whole of that range. What they mean is that there's a 3 megahertz range, and as I said before, the bandwidth is about 200 kilohertz, and so you can get about 15 channels, all transmitting radio 2 at varying points between 88 and 91. And the reason for that is that you cannot have two transmitters side by side transmitting at the same frequency. Otherwise, the person in the middle, when they listen on their radio, will get interference. And so adjacent transmitters always have to transmit on different channels. And you've got 15 to choose from. So that by the time you've got to a transmitter 15 away, you can go back to using the same frequency as you used for the first transmitter, but by now it's going to be so far away there's going to be hardly any interference. Signals that are sent by microwave in the EHF region are usually used for point-to-point contact, and the way they are caught, transmitted and caught, is by using parabolic dishes. Now the dishes are not the transmitters and the receivers, they're just the means by which the information gets sent. There will be a transmitter and a receiver at the focal point of this parabola, and what happens is the signal gets sent out, and when it hits the other it goes in like that. So you've got transmission coming this way, the mirror pushes it out, and then when it gets to the, as it were, the parabolic dish or mirror at this end, these are microwaves, not light waves, the rays are focused in on the receiver. So you've got a transmitter and a receiver, but it's the dishes that help with the transmission. And then finally you've got optical fibres, which we've shown in another video, operate because you've got total internal reflection going on. The light never comes out, it's always constantly being reflected, and you can what's called attenuate the light pulses that you send through to effectively encapsulate the signal of the sound you're trying to transmit. And optical fibres have the capacity to transmit many thousands of signals at once, so they're very efficient at carrying information. And they suffer from very much less interference. But of course, you do need a long optical fibre if you're going to communicate over long distances, which is why you have to decide which is your best option, and that's why for very long distance transmission, it's better to go for broadcast, where you transmit over the airwaves. Satellites can also be used to compensate for the curvature of the Earth. If we have a transmitter here and a transmitter here, they're not in line of sight, and so the signal cannot transmit directly from one to the other. But if you have a satellite in the air, then you can send the signal up to the satellite, and the satellite sends it back down to another receiver, and the information can then go around the world. And typically this information will be sent up on the 6 gigahertz frequency, and it comes down on the 4 gigahertz frequency. It has to come down on a different frequency, of course, otherwise there's a risk that the two would interfere. Of course, in order to do that, the satellite has got to remain in that position relative to the Earth the whole time. And the way it does that is it is in what's called, here's the Earth, there's the equator, and the satellite is in what's called a geostationary orbit, which simply means that the satellite orbits once every 24 hours in exactly the same way as the Earth rotates once every 24 hours. So if the satellite is rotating at the same speed as the Earth, or rather at the same angular velocity as the Earth, then it will appear to remain over one point of the Earth for the whole time. Now, a geostationary satellite can only operate over the equator. That's the only place it can be. And then what you do is you transmit your signal up to that satellite and back down to another receiver on the Earth. A geostationary satellite. And in a previous video we've calculated the height that needs to be. It's about 22,000 miles above the Earth in order for the orbit to be exactly 24 hours. I should of course give you the height in kilometres. It's about 36,000 kilometres above the Earth, or 22,000 miles. When a signal travels along a wire, it loses power. The reason is that all sorts of things are happening. For example, the electrons are moving, vibrating, creating heat. Heat is being lost, and so as you lose power, so the power of the signal strength will reduce. For that reason, you need to put an amplifier in the circuit which sends out a much more powerful signal. And if we call the power out P1 and the power in P2, then the number of bells is the logarithm of P1 divided by P2. But we don't talk about bells, we talk about decibels. So the number of decibels is equal to 10 times the log of P1 over P2, because there are 10 decibels in one bell. So if you know what is known as the gain of the amplifier, which is the number of decibels, and you know what the power in is, P2, then the only thing in this equation you don't know is P1. You can calculate the power. Similarly, you can say, well, let's not bother about an amplifier. Let's just take power starting along a line and ending up with P1, because we've lost heat and other forms of energy along the way. Once again, if you know what the attenuation is, which is the opposite of gain, because instead of gaining power, as you do with an amplifier, you lose it, that's called attenuation. If you know what the attenuation is in decibels, and you know what the starting power was, you'll be able to work out what the end point is going to be. Now, the further you travel along that wire, the greater will be the attenuation, and eventually you'll get to a stage where the power of the signal that you want is comparable to the sort of the noise that is inherent in the wire, and then you won't be able to make out the signal anymore. So you need to keep a minimum signal to noise ratio. That is to say that the level of this signal must always be a certain number of times greater than the inherent noise which is in the wire. And once again, that signal to noise ratio can be expressed by the decibels, and that tells you what P1 and P2 can be. And if you know how the attenuation is affected by the length of the wire, then you can work out the maximum length of a wire you can use before the P1 gets down to an attenuation, which is the minimum signal to noise ratio. How do telecommunications work? How does the telephone system work? Well, in the old days, it was all on cables. So you would have lots of people with individual telephones, and those would all be connected by individual wires to a local exchange. That local exchange might go to a trunk exchange, and that might go to an international exchange before going back to whoever. So if you were calling someone locally, you would simply be routed by, in those days, relays from the local exchange to the person you wanted to talk to. Those two people could talk to like that. If you wanted to talk nationally, then the local exchange would go to the national exchange, which would go to another local exchange, which would connect you to somebody living some way away from you. And similarly, if you go internationally, then you go to an international exchange, to a trunk exchange, to a local exchange, to a telephone. And that was the old public switch telephone network, the PST, public switch telephone network, PSTN. Now, of course, we have mobile telephones which aren't connected to anything, and they transmit to a local base station, which is then connected to a cellular exchange, and that may itself be connected to the public switch telephone network, and that enables you to call from a mobile onto a landline. The power you can get for transmission from a mobile phone is not very much, and therefore the receiving aerial has to be fairly close. That's why you have to have so many receivers in an area to pick up mobile phone signals, because those signals have got to reach the television, have got to reach the receiver for the mobile telephone. And the mobile telephones therefore will have lots of receivers. But those receivers are also transmitters. They're sending information back to the phones. But as we know, they can't all be transmitting on the same frequency, otherwise you'll get interference. So once again, you have to have a series of different transmitter frequencies around the country. So for example, in one location, you might have one particular frequency, but in the next adjacent location, you have frequency 2, in adjacent frequency here 3, here you have to have another one again, 4, here you have to have another one again, 5, here another one again, 6, here another one again, 7. But now, once you get to here, you might be able to use 6 again, because it's far enough away that people can't interfere. When you switch on your mobile phone, wherever you happen to be, if you happen to be standing here, then what will happen is that the number 1 transmitter receiver will discern that your signal is the strongest, and you will be connected to the number 1 transmitter. But if you are travelling in your car, then when you get to here, the number 1 will detect that the signal has gone very faint, and number 3 will detect that the signal has become very strong. And so you will be, as it were, diverted onto, you don't even realise this, but now transmitter receiver number 3 is handling your transmission. And all of these transmitter receivers are, of course, connected to the central exchange, which itself is connected to the PSTN. And then finally, we need to know how a mobile phone works. Well, at its heart, of course, a mobile phone must have a microphone, that's what you speak into, and a loudspeaker, which is the earpiece, as it were, that you can hear from. And at the other end, you have to have an aerial. That aerial is usually embedded now within the telephones. It only needs to be very short. And you are then sending your signal from the microphone to the aerial. That's to get the signal to go. And then you use the same aerial to receive the incoming signal, which gets sent to the loudspeaker. But what is the process between the two? Well, to start off with, when you have a microphone, you're going to need an amplifier to amplify the signal. Then you need, that's going to be an analog signal. It's going to be electrical pulses that reflect or are analogous to your voice. You then have to go to an analog to digital converter, and now we've got a digital signal. Now you have to go to what's called a parallel to serial converter. What is happening is that this analog to digital converter is producing a frame's worth of information at a time. You remember the freeze frame of the electrical signal is converted into digits, and you get an array. But you can't send an array, you have to send the numbers, the digital numbers, one by one. And so the parallel to serial converter actually gets that stored array and converts it into a long line of digital information. That then has to be added to the carrier wave, which is going to carry the information from the aerial. And finally, you need to amplify it again and send it to the aerial to be transmitted to the local receiver that will receive the information. Now, when someone replies to your telephone call, the information is received from the aerial. It first has to go to a tuning circuit, which will make sure that it is connected to the frequency of the transmitter that is sending the information in the first place. You then have to, as it were, de-amplify, reduce it. You then have to put it through a demodulator, which essentially takes off the carrier wave and just leaves the basic digital signal. You then have to send it to a serial to parallel converter, which is the opposite of the parallel to serial. In other words, it puts all the digital information back in its array form again. Then you can go to the digital to analog converter. So now you take the digital information and you convert it into an analog electrical signal, and that then is sent to another de-amplifier, which sends it to the loudspeaker, which gives the information that comes into your ear. And we're going to have a loudspeaker. How do they work? Well, my video on electromagnetism will give you the clue there. Basically, what you're talking about is if you move a magnet, here's a magnet, a bar magnet, if you move a magnet in a coil of wire, a current will flow. Or you move a coil of wire in the presence of a magnet, a coil will flow. And so the way a microphone works is you have what's called a diaphragm, which is rather like a stretched piece of plastic, like, for example, a balloon skin. And in the middle you place a very small magnet, and then around it you have a coil of wire. Then if you've got sound waves coming, those sound waves are oscillating, vibrating waves, and as they hit this essentially balloon diaphragm. Hello, today we're continuing in our A-level physics revision series, this time looking at telecommunications. We can of course communicate by using our voices, and somebody else can listen through their ears. In that case, sound is travelling from the voice to the ear. Sound waves are longitudinal waves, that is to say that the air in between the voice and the ear is vibrating backwards and forwards, and that's a longitudinal wave. So you've just got air molecules that are vibrating. But that's not necessarily the best way of communicating. You might be too far away to be heard. So now you need to use a microphone and a speaker. So here we are. And now we're going to use a microphone. It requires that the microphone and the speaker is connected by a wire. And once again, that may be too far away. So now you may need the microphone and the speaker to be connected by telecommunications, which is when you send signals through the air. And that's what we're principally going to be looking at in this video. How do you send and receive signals through the air? Well, you use either a transmitter or an aerial, and in each case they're the same thing. They're basically just a length of wire. And what you do is you apply a varying, alternating voltage to this wire. And when you apply a varying voltage, then the voltage on the wire will change. And as a consequence, the electrons in the wire will be attracted to the positive end of the wire. The diaphragm vibrates, the magnet itself, which is connected to the diaphragm, vibrates, and a vibrating magnet in the presence of a coil of wire will cause a current to flow. And that's how a microphone translates sound into an electrical signal. The loudspeaker is simply the same thing, but in reverse. The loudspeaker takes the electrical signals from the microphone. The electrical signals are in the coil of wire. They're varying electrical impulses, and a changing current will cause a magnet to move. And so the magnet now moves, and that creates oscillations, and those oscillations will then cause the air molecules to oscillate, and oscillating air molecules emerge as sound. But of course all of that, so when the voltage is at the positive end, the electrons will all shoot up this way, and when the aerial is negative, the electrons will shoot down that way. And so the electrons are constantly accelerating up and down the wire. And what happens when a charged particle accelerates, you should know that generates an electromagnetic wave. And the frequency of that electromagnetic wave will be the same as the frequency of the electrons shooting up and down this wire, which of course is the frequency of this voltage here. And it's exactly the same, but in reverse. When you get to the receiver, the wave comes in, it causes the electrons in the wire to vibrate up and down, and that creates a voltage pulse, which then can be sent off to the